Hi everyone, today we will show you how to use the Haar Cascade algorithm for detecting objects in the real world. And it is a zero-shot detection model, which means you can detect objects in real time. Especially, our team will detect personal protective equipment like safety hat and gloves. This project was carried out by our team members Jade, Wei, and Chakripani under the guidance of Dr. Paar. Personal protective equipment plays a vital role preventing injuries, reducing health risk, and saving lives in high-risk industries. However, ensuring consistent PPE compliance through manual monitoring methods can be tedious, cost-intensive, and difficult to scale effectively. To address these challenges, we propose an automated system for detecting PPE. By transforming manual PPE inspection processes into an intelligent, automated workflow, like our solution not only mitigates safety risk but also optimizes resource allocation, at the same time improved overall operational efficiency. The core objective is to create a reliable model that provides comprehensive and consistent safety monitoring. Ensuring workplace safety is upheld at all times. This image is one of the examples for implementing our algorithm. By harnessing the power of computer vision, we are data-driven protection way approach workplace safety for industrial workers. Many open source datasets are sourced from platforms through web crawling with search engines such as Google or Bing. And we also include various existing datasets for the PPE detection. Some notable datasets are the SHW dataset, which includes around 7,000 images and over 120,000 instances. And the other famous one is GDUT HWD dataset with around 3,000 images and nearly 19,000 instances. And then we cleaned the dataset with 8 main features over 8,000 images, so total approximately 76,000 instances. Our dataset categorizes key elements associated with PPE detection. We've calculated a lovely statistic first. The chart on the right illustrates the distribution of instances across categories, with hands being the most frequently detected, with over 16,000 instances, followed by persons and heads. Also, we included additional tags to improve detection accuracy, such as tools or shoes are on or off, and the color of helmets. At the bottom side image, we have examples of our datasets in action, showing the model detecting multiple PPE items in diverse scenarios, such as construction sites and solar panel installations.
Hi, I'm Chakrapani Yegatila. Today I'm going to discuss about the core algorithm that is used to detect the presence of a PPE such as PPE and gloves, helmets, etc. The algorithm used is Haar Cascade algorithm. So you can see it in the image that we are using several Cascade pools which are fed into different stages these stages are either responsible for detecting certain features of an image. Let's say the image has both clouds and PPE. So stage 1 is responsible for detecting the PPE, stage 2 is responsible for detecting the clouds, and several stages like that which are used to detect several things. So each stage outputs has two things, which is fail. If it is not there, then it straight goes into the rejection. If it is there, then it gets forwarded into the next region. Haar Cascade algorithm is an algorithm that can detect objects and images irrespective of their scale in image and location. They use Haar features to determine the likelihood of a certain point being a part of an image. On the left hand side, we can see the different Haar features that are present. We have edge features, line features, center surround features, and four rectangle features. So individually, these features, these singular edge features can't alone detect an object in an image. So we combine all these things, like these features individually are weak. So we combine all these features together to form a boosting algorithm. Cascading classifiers are used to run boosting algorithms on different subsections of an image. Every image can be split into varying image subpixels with different intensities. The darker areas in the Haar feature are pixels with values 1, and the lighter areas are pixels with value 0. Each of these is responsible for finding out one particular feature in the image, such as an edge, a line, or any structure in the image where there is a sudden change of intensities. For example, in the image, the Haar feature can detect a vertical edge with darker pixels at its right and lighter pixels at its left. The main objective is to find out the sum of all image pixels lying in the darker area of the Haar feature and the sum of all the image pixels lying in the lighter area of the Haar feature, and then find out their difference. If the image has an edge separating dark pixels on its right and light pixels on the left, then the Haar value is closer to 1. That means there is an edge detected if if the Haar value is closer to 1. In the figure there is no edge, as the Haar value is minus 0.02, which is very far away from 1. In the previous slide, we calculated the sum of all the different intensities of darker and lighter subpixels. That takes a lot of additions when we are doing it in a large scale. To speed up the process, the integral image method is used. This is similar to what we learned in the class in the dynamic programming lecture in engineering analysis class, where we find out the shortest distance from one place to another using the Google Maps example. This is analogous to that. An integral image is calculated from original image in such a way that each pixel is the sum of all the pixels lying in its left and above in the original image. You can see in the GIF presented here, we have 0 0.4 and 0 0.3 at the top left. So when we are doing the integral image method, we add the 0 0.4 to the 0 0.3 subpixel, so it becomes 0 0.7, and then we go to the top right at like 0 0.7 again, and we add zero point 0.7 to that, and we add like this to get the whole Haar image map. When we do this integral image method, we only need four constant value additions to find out any feature size. In the previous case, it used to be 18. So this is a lot of reduction, which saves a lot of time. By using the integral image method, the last pixel at the bottom right corner will be the sum of all the pixels in the original image. Since all the images are added together at the beginning, this reduces the time complexity of each addition gradually, as the number of additions does not depend on the number of pixels enclosed anymore. Now, when we calculate the sum of pixels in the light area and the darker area, we get less number of additions, which will save us the time. Also, this is how we find out the Haar features, and these are only the primitive features. When we wanted to find out an entire image, we have to do like several stages of it. So we go for adder boosting to enhance the speed of the model. Adder boost selects the best features and builds a strong classifier by combining multiple weak classifiers. Multiple weak classifiers include edge features, line features, rectangle center surround features. To do the adder boosting, we first initialize the weights. We assign equal weights to all the training samples. Let's say we have positive samples, which means there is a PPE inside the image, and we have negative samples, which does not have any PPE or like clauses in the image. And then we iterate it over a number of rounds by selecting various different weak classifiers. Then we train the weak classifiers, and then we compute the weighted error. We do the train test split to see if how many weak classifiers are having how much different error. And then by looking at these errors, we select the best weak classifier which has the lowest error. And and then when and then we again compute the classifier weight. Now a lower error leads to a higher weight. Now we'll be updating the sample weights, and we normalize the weights. Since now all these classifiers have different weights, now we are finally ready to have one strong final classifier that is mentioned in the equation is mentioned in the PPT. This combination of adder boost and Haar features allows Haar Cascade to be highly efficient and accurate for object detection tasks.
Hello everyone, my name is Wei Lam. I'm present and take responsibility in the parts of research, discussion, conclusion, and summary. This slide shows the category accuracy of our trade model. So in this table, there are different kind of model like category, instant precision, recall, and mean average precision. So in the first row, there are different type of category like they are related to PPE system. For example, hand, parts and head, face, ear, and so on. So we also had a different number of instance. So for the precision part, we had the higher precision values, 96%. That's it for face, and we had 67.4%. That is the lowest in two. So for the recall parts, we had the highest recall values is 89.2% in percent, and the lowest recall percent is 39.1%. That's it for two saying. Uh, this slide presents the training method of high cascade model. In this slide, there are four parts of category: the precision, the recall, mean average precision, 0.5, 0.5 to 0.95. So for the top two graphs, the precision and recall, they improve steadily during the training and indicating the model. So for the parts of mean average precision, so when I evaluate detection with an IOU threshold of 50%, it gets a higher value that present better performance. After that, when I run with from 50% to 95%, the volume are lower, but I got a more accurate measure of model performance. In this slide, we want to show the accuracy rate of our algorithm. So we run different kind of video with the different frame with the different quality. For example, the first video is posted 28,000 frame. Is it a good quality? So for the second video edit process, that video is negative video, 4 is negative video 2. The first one is the background video. So in this testing, we get two good quality video in video 1 and video 5. Is it the posted video and the background video? So we got for the first video is accuracy at 100%, and the background video is almost 100%. Is it 0.965%? But the last three video 2, video 3, video 4, we got the average percent is around 0.72%. Because in this video 1 and video 5, we get with different quality. Is it the good quality? It means like the video is clear, the light and the shadow of the video are really good, and the complexity is low. That's it. The one, the accuracy rate of the video 1 and video 5 is so high in this testing. This slide represents the visual results of inference on dataset. It shows like the way it's detected on database as we train in data, like the hand, person, head, face, shoe, hammers, and so on. So it's a different kind of construction, different kind of working place like education, agriculture, industry, and so on. This slide represents discussion and conclusion. In this model, we got a wide range accuracy as we testing with the 5 video. For example, the first video and the 5 video, we received almost 100% accuracy, while the video 2 received 71.24%. The video quality, the lighting condition, and the object occlusion also affects on the accuracy of this model. For the framework, is it also play a larger role in the model performance? The overall model perform very well, but the accuracy for 2 and shoe are really low when we compare with other category. But we can improve this category by addressing their specific challenges. For the future work, we can involve fine-tuning Haar Cascade with more diverse data set. We can incorporate with advanced techniques like deep learning, optimize its performance for the complex object. This is the summary of our presentation. We studied the needs of automation in system equipment for a high-risk environment. So we employed the Haar Cascade algorithm to identify system gear sets at PPE and the hammers. We understood in detail how the Haar Cascade algorithm works. We also observed how the algorithm is developed in real time and measure the accuracy of the model. We need a lot of training data to get a higher, better results and a higher accuracy. Finally, I would like to say thank you to my professor for teaching and guiding us during this semester. And I also want to say thank you to my classmates because we had a great time together. Thank you, everyone.